For centuries, astronomers have stared into the darkness between Mars and Jupiter, puzzled by a broken ring of shattered worlds. Some believe these fragments are the remains of something far greater, a forgotten planet called Phaeton, a world that may have once existed and then violently disappeared from the solar system. But what happened to it? And why does its story feel more like a cosmic warning than a simple scientific mystery? According to ancient legends, Phaeton was a bright, wandering star that fell from the heavens. Modern theories suggest something eerily similar, a planet torn apart by forces so powerful they rewrote the architecture of our solar system. Was it destroyed by a catastrophic collision? Ripped apart by Jupiter's gravity? Or did something even stranger take place? Something we still don't fully understand? Do not forget to leave a like and subscribe to the channel, as tonight we are diving into the forgotten history of a world that may have once been real. A world that left behind only silence, dust, and a trail of cosmic clues. This is the mysterious story of Phaeton, the lost planet that shouldn't exist, yet might explain more about our solar system than anything we've discovered so far. Get ready, we begin. When you look up at the night sky on a clear evening, you see thousands of stars scattered across the darkness, and maybe a few bright planets moving slowly through the constellations. For thousands of years, humans watched these wandering lights and wondered what they were, creating stories and myths about gods traveling across the heavens. The ancient astronomers knew of 5 planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. They tracked these celestial wanderers with precision, noting their movements and predicting their positions years in advance. But between Mars and Jupiter, there was only darkness, a vast empty gulf where no planets seemed to exist. For centuries, this gap in the solar system remained unquestioned. No one thought to look for anything between these 2 planets because the very idea seemed unnecessary. Mars marked the boundary of the inner rocky planets, while Jupiter stood as the first of the giant outer worlds. The space between them appeared to be just that: empty space, a cosmic void separating 2 very different realms of our solar system. This understanding would persist until the late 18th century, when mathematical patterns began to suggest something remarkable might be hiding in that darkness. In 1766, a German astronomer named Johann Daniel Titius published a curious mathematical relationship that seemed to predict the distances of planets from the Sun. Titius had noticed that if you took the number 4 and added certain values in a geometric sequence, then divided by 10, you could approximate the distance of each planet from the Sun in astronomical units. The sequence started with Mercury at 4, Venus at 7, Earth at 10, and Mars at 16. Following the pattern, the next planet should be at 28 astronomical units, but no planet was known at that distance. The pattern was elegant and simple, but it was also incomplete. Between Mars at 16 and Jupiter, which should have been somewhere around 52 according to the pattern, there was a gap at 28 where the mathematics insisted a planet ought to exist. For years, this observation remained little more than a mathematical curiosity, discussed among astronomers but not taken seriously as a predictive tool. After all, mathematics could create any number of patterns, and just because numbers aligned in an interesting way did not mean the universe was obligated to follow them. Everything changed on March 13th, 1781, when William Herschel made one of the most important astronomical discoveries in history. While searching for double stars using his homemade telescope in Bath, England, Herschel noticed an unusual object in the constellation Gemini that appeared as a disk rather than a point of light. At first he thought it might be a comet, but as he continued his observations, the object's behavior seemed wrong for a comet. It moved too slowly and too uniformly, following a nearly circular path around the Sun. After weeks of verification and consultation with other astronomers, including the astronomer Royal Neville Maskelyne, the stunning truth became clear. Herschel had discovered a new planet, the first planet to be found using a telescope rather than naked eye observation. This distant world, eventually named Uranus, orbited the Sun far beyond Saturn, at a distance of approximately 19 astronomical units from the Sun. When astronomers checked this distance against the Titius-Bode law, as the mathematical relationship had come to be known, they found something astonishing. Uranus was almost exactly where the pattern predicted it should be. This remarkable confirmation transformed the Titius-Bode law from mathematical curiosity into scientific prophecy. If the pattern could predict the location of an unknown planet with such accuracy, then perhaps it truly did reveal some fundamental structure of the solar system. And if that were true, then the gap at 28 astronomical units between Mars and Jupiter could not be empty after all. Somewhere in that darkness, the pattern insisted, there had to be a planet waiting to be discovered. The discovery of Uranus ignited an astronomical revolution. Across Europe, astronomers turned their telescopes toward the region between Mars and Jupiter, systematically searching the sky for the missing planet. The task was enormous and daunting. Unlike the bright, obvious disk of Uranus, which Herschel had spotted almost by accident, the hypothetical planet between Mars and Jupiter would be much smaller and fainter. It might take years of careful observation to find, requiring patience, dedication, and no small amount of luck. In 1796, a group of astronomers formed what they called the Celestial Police, a collaboration dedicated to finding the missing planet. They divided the zodiac into sections, with each astronomer responsible for carefully mapping the stars in their assigned region and watching for any object that moved against the fixed background of stars. The search was methodical and scientific, representing a new approach to astronomy where systematic observation replaced the chance discoveries that had characterized earlier eras. These astronomers knew exactly what they were looking for and roughly where to find it, thanks to the Titius-Bode law. One of the astronomers recruited for this search was Giuseppe Piazzi, a Catholic priest and professor of mathematics at the Academy of Palermo in Sicily. Piazzi was not yet part of the Celestial Police when fate intervened. On the very first night of the 19th century, January 1st, 1801, Piazzi was working on creating a new star catalogue, carefully recording the positions of stars in the constellation Taurus. He was specifically searching for a star listed in an earlier catalogue, but he found something unexpected, a faint point of light that appeared in his telescope but was not on any of his charts. At first, Piazzi thought he had simply discovered a previously unknown star. But when he observed the same region of sky the following night, he noticed something strange. The mysterious point of light had moved. Stars remained fixed in their positions relative to each other, but this object was clearly travelling against the background of stars, which meant it had to be something much closer than a distant sun. Piazzi's first thought was that he had discovered a comet, those icy wanderers that occasionally sweep through the inner solar system. Comets were valuable discoveries, and finding one would bring prestige to any astronomer. However, this object did not behave like any comet Piazzi had ever seen. Comets typically appear fuzzy and indistinct through a telescope because they are surrounded by a cloud of gas and dust. This object appeared as a sharp point of light, like a distant star or planet. Its motion was also wrong for a comet. Comets move in long elliptical orbits, often travelling very quickly when they pass near the Sun. This object moved slowly and steadily, suggesting it was in a more circular orbit. For 41 nights, Piazzi tracked this mysterious object across the sky. He measured its position carefully each night, noting how it moved relative to the background stars. The object travelled from west to east, then appeared to slow down, stop, and reverse direction before illness forced Piazzi to stop his observations on February 11th. By this time, he was convinced that he had discovered something extraordinary, something that might be the missing planet everyone was seeking. Piazzi wrote letters to several prominent astronomers, including Barnaba Oriani in Milan and Johann Bode in Berlin, describing his discovery. In his letters, he was cautious, describing the object as possibly a comet, but noting that its slow, uniform motion suggested it might be something better. When Bode received Piazzi's letter and examined the observational data, he immediately recognized the significance of what Piazzi had found. The object's estimated distance from the Sun placed it almost exactly where the Titius-Bode law predicted the missing planet should be. News of the discovery spread rapidly through the European astronomical community, creating enormous excitement. After 20 years of searching, it seemed that the missing planet had finally been found. However, there was a problem. By the time Piazzi's observations were published and other astronomers learned about the discovery, the object had moved into the daytime sky where it could not be observed. Without more observations, astronomers could not calculate a precise orbit, and without a precise orbit, they had no way of knowing where to look for the object when it emerged from behind the Sun. This is where Carl Friedrich Gauss, a young German mathematician who would become one of the greatest mathematicians in history, made his entrance into the story. Gauss had recently developed a new method for calculating orbital elements from just a few observations, a mathematical technique that was far more accurate than anything available before. Using only Piazzi's limited observations from 41 nights, Gauss calculated where the object should reappear when it emerged from the Sun's glare. His prediction was remarkably precise. On the last day of 1801, nearly a year after Piazzi's initial discovery, the German astronomer Franz von Zach found the object almost exactly where Gauss had predicted it would be. This successful recovery confirmed that Piazzi had indeed discovered a new member of the solar system. Heinrich Olbers, another German astronomer, also independently recovered the object on the first day of 1802. The astronomical world celebrated this triumph of mathematical prediction and careful observation. Piazzi had already chosen a name for his discovery: Ceres Ferdinandea, combining Ceres, the Roman goddess of agriculture and grain, with Ferdinand, honouring King Ferdinand of Sicily. The name was eventually shortened to simply Ceres, though the full name appeared in some early publications. Astronomers immediately declared Ceres to be the 8th planet of the solar system, the missing world that the Titius-Bode law had predicted. However, as more astronomers turned their telescopes towards Ceres, doubts began to emerge. Even through the most powerful telescopes available at the time, Ceres appeared as nothing more than a point of light. Unlike the other planets, which showed clear disks when viewed through a telescope, Ceres remained stubbornly star-like in appearance. This suggested that Ceres was far smaller than any other known planet, possibly smaller even than Earth's moon. William Herschel, the discoverer of Uranus, was among the first to express skepticism about Ceres's planetary status. He argued that an object so small should not be called a planet at all, and suggested the term asteroid, meaning star-like, to describe this new class of objects. Despite Herschel's objections, most astronomers continued to refer to Ceres as a planet, and it appeared in astronomical textbooks and solar system diagrams as the 5th planet from the Sun. The controversy over Ceres' status was still unresolved when Heinrich Olbers made another startling discovery. On March 28, 1802, just 3 months after recovering Ceres, Olbers found another moving point of light in almost the same region of sky. This second object, which would be named Pallas after the Greek goddess of wisdom, was very similar to Ceres in size and appearance. It orbited the Sun at nearly the same distance as Ceres, and like Ceres, it appeared as a mere point of light even through powerful telescopes. The discovery of Pallas created a significant problem for the Titius-Bode law and for the idea of a single missing planet. The mathematical pattern predicted one planet at the 28 astronomical unit position, not two. How could there be two planets sharing the same orbital space? Some astronomers suggested that perhaps both Ceres and Pallas deserved planetary status, making the solar system a realm of 10 planets rather than 9. Others began to wonder if these objects represented something entirely different from traditional planets. The situation became even more complicated over the following years as more discoveries followed. In September of 1804, German astronomer Carl Harding discovered Juno, a third object in the Mars-Jupiter gap. 3 years later, in 1807, Heinrich Olbers found Vesta, a fourth member of this growing family of small worlds. By 1810, the region between Mars and Jupiter contained 4 known objects, all of them tiny compared to traditional planets, all of them sharing roughly the same orbital distance from the Sun. For several decades, these 4 objects were classified as planets, giving the solar system a total of 12 known planets, including Vulcan, the hypothetical planet between Mercury and the Sun that some astronomers believed existed. Astronomy textbooks from this era show diagrams of the solar system with all 12 planets labelled and described. However, this classification was increasingly uncomfortable for many astronomers. These objects between Mars and Jupiter were clearly different from the other planets. They were much smaller, they shared the same general orbital space, and their numbers seemed to be growing. The debate over how to classify Ceres, Pallas, Juno, and Vesta might have continued indefinitely if not for another major discovery that would shake the foundations of the Titius-Bode law. By the early 19th century, astronomers had noticed irregularities in the orbit of Uranus. The planet was not moving exactly as mathematical predictions suggested it should. Something was perturbing its orbit, pulling it slightly off course. Several astronomers proposed that these irregularities might be caused by the gravitational influence of yet another planet, an 8th planet orbiting beyond Uranus. If such a planet existed, its position could be calculated by working backward from the perturbations it caused in Uranus's orbit. This was an ambitious proposal requiring sophisticated mathematical analysis, but 2 mathematicians took up the challenge independently: Urbain Le Verrier in France and John Couch Adams in England. Both mathematicians performed extensive calculations, attempting to determine where this hypothetical 8th planet should be located. Their predictions agreed remarkably well with each other, pointing to a specific region of sky where the unknown planet ought to be visible. On September 23, 1846, German astronomer Johann Gottfried Galle pointed his telescope at the predicted location and immediately found a new planet, confirming the mathematical predictions with stunning accuracy. The new world was named Neptune, after the Roman god of the sea. The discovery of Neptune represented another triumph of mathematical astronomy, proving that the laws of gravity and motion could predict the existence of unknown worlds. However, Neptune also dealt a fatal blow to the Titius-Bode law. When astronomers calculated Neptune's distance from the Sun, they found it orbited at approximately 30 astronomical units, far closer than the law predicted. According to the Titius-Bode pattern, Neptune should have been around 39 astronomical units from the Sun, but it was not. The pattern that had seemingly predicted Uranus and the asteroid belt with such accuracy failed completely for Neptune. With Neptune's discovery, astronomers began to reconsider the Titius-Bode law. They realized that the law's apparent successes might have been coincidental rather than revealing any deep physical principle governing planetary spacing. The pattern worked reasonably well for the inner and middle planets, but broke down for the outer solar system. Modern analysis has shown that the Titius-Bode law is not a fundamental law of nature, but rather a numerical coincidence that happens to approximate some planetary distances while failing for others. The failure of the Titius-Bode law had immediate consequences for Ceres, Pallas, Juno, and Vesta. If the mathematical pattern that predicted their existence was not valid, then there was no particular reason to believe a planet should exist in the Mars-Jupiter gap. The four small objects could be explained more simply as something other than planets. In 1854, astronomers began using William Herschel's term asteroid to describe these bodies, demoting them from planetary status. This reclassification reduced the solar system back to 8 known planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. The demotion of Ceres and its companions raised interesting questions about the nature of these objects and how they came to be. If they were not fragments of a planet, or planet-sized worlds in their own right, what were they? Why were there so many of them clustered in the same region? As telescopes improved throughout the 19th and 20th centuries, astronomers discovered hundreds, then thousands, then tens of thousands of asteroids in the region between Mars and Jupiter. This vast collection of rocky debris became known as the asteroid belt, a distinct region of the solar system unlike anything else. Heinrich Olbers, the astronomer who discovered both Pallas and Vesta, proposed an explanation for the asteroid belt that captured imaginations for more than a century. Olbers suggested that the asteroids were fragments of a larger planet that had once existed in the Mars-Jupiter region. This hypothetical planet, which would later be called Phaeton, after a figure from Greek mythology, had somehow been destroyed, shattered into thousands of pieces that now orbit the Sun as asteroids. The shattered planet hypothesis was elegant and dramatic, offering a simple explanation for why so many small objects shared the same orbital space. Olbers imagined that billions of years ago, a planet roughly the size of Mars orbited the Sun between Mars and Jupiter. This world would have been cold and distant from the Sun, perhaps covered in ice like some of Jupiter's moons. For some reason, catastrophic destruction befell Phaeton, breaking it apart and scattering its fragments throughout the region. What could have destroyed an entire planet? Olbers and other 19th century astronomers proposed several mechanisms. Perhaps Phaeton was struck by a massive comet or asteroid, an impact so violent that it shattered the entire world rather than simply creating a crater. Perhaps Jupiter's immense gravitational pull had torn Phaeton apart through tidal forces, the same way Jupiter's gravity tears apart comets that venture too close. Some even suggested internal mechanisms, proposing that Phaeton might have exploded from within due to some catastrophic geological process. The idea of a destroyed planet resonated with scientists and the public alike throughout the 19th and early 20th centuries. It explained the asteroid belt in simple, understandable terms and provided a dramatic story of cosmic violence and planetary destruction. Some versions of the hypothesis even suggested that the destruction of Phaeton might have been relatively recent in geological terms, perhaps occurring within the last few million years rather than billions of years ago. However, as astronomers learned more about the asteroid belt and developed more sophisticated understanding of planetary science, the Phaeton hypothesis became increasingly difficult to support. The first problem was mass. When astronomers calculated the total mass of all known asteroids, they found it was far too small to represent the fragments of a planet. Even if you gathered together every asteroid in the belt and combined them into a single body, the resulting object would have a mass of only about 4% of Earth's mass, much smaller than any planet. The composition of asteroids also posed problems for the shattered planet hypothesis. If the asteroids were fragments of a single planet, they should all be made of similar materials, representing different parts of the planet's interior and crust. Instead, astronomers found that asteroids show a wide variety of compositions. Some are rich in silicate rock, others are carbonaceous with high carbon content, and still others are metallic, composed primarily of iron and nickel. This diversity of composition suggests that asteroids formed separately from different materials rather than originating from a single parent body. Furthermore, the orbits of asteroids proved difficult to reconcile with a planetary destruction scenario. If all the asteroids originated from a single shattered planet, their orbits should be relatively similar, all crossing through the region where the planet had been. Instead, asteroid orbits show considerable variation in inclination and eccentricity, more consistent with a population of objects that formed separately and have been perturbed by gravitational interactions over billions of years. Modern understanding of the asteroid belt comes from decades of detailed observations, spacecraft missions, and theoretical modelling of solar system formation. The current scientific consensus is that the asteroid belt never formed a planet at all. Instead, the asteroids represent leftover building material from the formation of the solar system, planetesimals that never accreted into a larger world because of Jupiter's gravitational influence. The story of the asteroid belt begins 4.5 billion years ago, during the earliest days of the solar system. At that time, the Sun was a young star surrounded by a vast disk of gas and dust called the solar nebula. Within this disk, particles of dust and ice began to stick together through a process called accretion, gradually building up larger and larger objects. Small dust grains became pebbles. Pebbles became boulders. Boulders became mountain-sized chunks of rock and ice called planetesimals. In most regions of the solar nebula, these planetesimals continued to collide and merge, building up ever larger bodies. In the inner solar system, where we now find Mercury, Venus, Earth, and Mars, planetesimals accreted into protoplanets and eventually into the rocky planets we know today. In the outer solar system, planetesimals incorporated large amounts of ice along with rock, building up massive cores that eventually gathered enormous atmospheres of hydrogen and helium, becoming the giant planets Jupiter, Saturn, Uranus, and Neptune. The region between Mars and Jupiter should have followed a similar path. There was plenty of material in this area for a planet to form, and the process of accretion did begin. However, Jupiter's formation changed everything. Jupiter formed quickly, accreting mass rapidly and becoming a gas giant while the solar system was still very young. Once Jupiter reached substantial size, its powerful gravitational field began to dominate the region around it, extending its influence all the way into what would become the asteroid belt. Jupiter's gravity affected the asteroid belt region in several important ways. First, it increased the orbital velocities of planetesimals in the belt, causing them to collide with each other at higher speeds. When planetesimals collide slowly, they tend to stick together and merge, growing larger through accretion. But when they collide at high speeds, they tend to shatter and fragment instead of merging. Jupiter's gravitational stirring ensured that collisions in the asteroid belt were too violent for accretion to continue effectively. Second, Jupiter's gravity created orbital resonances throughout the asteroid belt. An orbital resonance occurs when the orbital period of one object is a simple fraction of another object's orbital period, such as 1 to 2 or 2 to 3. At these resonance locations, the repeated gravitational tugs from Jupiter add up over time, pumping energy into asteroids and either ejecting them from the belt entirely or moving them to different orbits. These resonances created gaps in the asteroid belt, regions where asteroids cannot maintain stable orbits. Third, Jupiter may have migrated inward through the asteroid belt region early in solar system history, a scenario called the Grand Tack hypothesis. According to this model, Jupiter formed farther from the Sun than its current location and then migrated inward due to interactions with the gaseous solar nebula. As it migrated, Jupiter would have scattered planetesimals throughout the asteroid belt, preventing them from accreting and also scattering much of the material out of the region entirely. Jupiter eventually reversed course and migrated back outward, but by then the damage was done and the asteroid belt could no longer form a planet. The result of these processes is the asteroid belt we observe today. Instead of a single planet, the region contains millions of small rocky bodies ranging in size from boulders to dwarf planets. The total mass of the entire asteroid belt is estimated to be only about 4% of the Moon's mass, a tiny fraction of what a planet would contain. This material is spread across an enormous volume of space, making the asteroid belt far less dense than popular culture often suggests. If you were to travel through the asteroid belt, you would most likely not see any asteroids at all with the naked eye, as they are spaced millions of kilometers apart on average. The asteroid belt is not a uniform collection of identical rocks floating in space. Instead, it contains a remarkable diversity of objects with different compositions, structures, and histories. Astronomers classify asteroids into several main types based on their composition, which can be inferred from their color and the spectrum of light they reflect. The most common type, representing about 75% of known asteroids, are C-type or carbonaceous asteroids. These objects are dark in color, reflecting very little sunlight, and are rich in carbon compounds. C-type asteroids are thought to be relatively primitive, meaning they have changed little since the formation of the solar system. They contain materials similar to the original solar nebula, including water ice and organic compounds. Most C-type asteroids are found in the outer regions of the asteroid belt, farther from the Sun. S-type or silicate asteroids make up about 17% of the asteroid population. These objects are brighter than C-types, with surfaces rich in silicate minerals and metallic iron. S-type asteroids are more common in the inner regions of the asteroid belt, closer to the Sun. They are thought to have been heated and partially differentiated early in their history, meaning their internal structure separated into layers with denser materials sinking toward the center. M-type or metallic asteroids are relatively rare, but scientifically fascinating. These objects appear to be made primarily of metallic iron and nickel, similar to the cores of rocky planets. M-type asteroids may be the exposed cores of larger planetesimals that were shattered by collisions, revealing their metallic interiors. Studying these objects provides insight into the structure of planetary cores that are normally hidden deep beneath layers of rock. Beyond these main categories, astronomers have identified numerous other asteroid types with unique compositions and properties. Some asteroids show evidence of water ice on their surfaces or contain significant amounts of frozen water inside. Others have surfaces rich in particular minerals or unusual ratios of different elements. This compositional diversity indicates that asteroids formed in different regions of the early solar system under different conditions, and that they have experienced varying degrees of heating, collision, and alteration over billions of years. The asteroid belt also contains objects of wildly different sizes. At the small end of the scale are countless boulders and pebbles, too tiny to be detected from Earth, but numerous enough that spacecraft traveling through the belt must account for them. At the large end is Ceres, by far the most massive object in the asteroid belt, with a diameter of about 950 kilometers. Ceres is so large that its gravity has pulled it into a spherical shape, making it a dwarf planet rather than a simple asteroid. Between these extremes are hundreds of thousands of asteroids large enough to be tracked and catalogued. Vesta, the second most massive asteroid, has a diameter of about 520 kilometers and a surprisingly complex geological history. Pallas, slightly smaller than Vesta, has an unusual highly inclined orbit that takes it far above and below the plane of the solar system. Hygeia, Interamnia, Europa, and dozens of other asteroids measure hundreds of kilometers across, large enough to be geologically interesting but too small to be considered dwarf planets. Of all the objects in the asteroid belt, Ceres stands apart as something special. When Giuseppe Piazzi discovered it in 1801, he had no way of knowing just how remarkable this object truly was. For more than 2 centuries, Ceres remained a mysterious point of light, too distant and too small to reveal its secrets through Earth-based telescopes. That changed dramatically in March of 2015, when NASA's Dawn spacecraft became the first mission to orbit a dwarf planet. Dawn's observations of Ceres revealed a world far more complex and active than anyone had expected. The dwarf planet has a layered internal structure, with a rocky core surrounded by a thick mantle of water ice. The amount of water ice contained within Ceres may be greater than all the fresh water on Earth, locked away in frozen form beneath a dusty surface. This discovery suggests that Ceres might have formed farther from the Sun, where water ice was more abundant, and later migrated to its current location in the asteroid belt. The surface of Ceres displays evidence of geological processes that may continue to the present day. The Dawn spacecraft discovered bright spots inside Fabia crater, which turned out to be deposits of sodium carbonate salt. These salts were likely deposited by briny water that welled up from Ceres's interior, suggesting that liquid water may exist beneath the frozen surface. The presence of this subsurface ocean, if confirmed, would make Ceres one of several ocean worlds in the solar system, joining moons like Europa, Enceladus, and Titan. Even more intriguing, Dawn discovered organic molecules on Ceres's surface, concentrated in the region of Ernetet crater. These organic compounds, which are building blocks for life as we know it, apparently originated from within Ceres itself, rather than being delivered by comet impacts. The combination of water, organic compounds, and geological activity raises fascinating questions about Ceres's past, and whether it might harbour conditions suitable for life in its subsurface ocean. Ceres also features a mysterious mountain called Ahuna Mons, a dome-shaped peak that rises about 4,000 metres above the surrounding terrain. This mountain appears to be a cryovolcano, a volcano that erupts ice and volatile compounds rather than molten rock. The existence of cryovolcanism on Ceres indicates that the dwarf planet's interior has remained warm enough to drive geological activity for billions of years, powered perhaps by radioactive decay or by tidal heating from gravitational interactions with other objects. The Dawn mission transformed our understanding of Ceres from a mere asteroid into a complex world with a rich geological history. Rather than a dead ball of rock, Ceres appears to be an active, evolving body that may have more in common with ocean moons like Europa than with typical asteroids. This realization has profound implications for how we think about the asteroid belt and the early solar system. If Ceres could retain heat and water for billions of years, what other surprises might be hiding among the asteroids? While Ceres represents water and ice, Vesta tells a very different story. When the Dawn spacecraft arrived at Vesta in July of 2011, it found a battered, scarred world that bore witness to billions of years of violent collisions. Vesta is the second most massive object in the asteroid belt, but unlike Ceres, it is a dry, rocky body with a structure remarkably similar to the terrestrial planets. Vesta's internal structure includes a metallic iron core, a rocky mantle, and a thin crust, just like Earth, Mars, or Venus. This differentiated structure indicates that Vesta was hot enough early in its history to melt, allowing denser materials to sink toward the center, while lighter materials rose to the surface. In this sense, Vesta is less like an asteroid and more like a miniature planet, a planetary embryo that never grew large enough to become a full-sized world. The surface of Vesta displays clear evidence of volcanic activity in its distant past. Ancient lava flows created vast, smooth plains in some regions, while volcanic vents and channels can be seen in high-resolution images. These volcanic features formed very early in solar system history, when Vesta's interior was still molten from the heat of its formation and from radioactive decay. Once Vesta cooled, volcanic activity ceased, leaving frozen evidence of this ancient epoch. But the most dramatic features on Vesta are its enormous impact craters. The southern hemisphere is dominated by the Rhea Silvia Impact Basin, a crater more than 500 kilometers in diameter, with a central peak that rises more than 20 kilometers above the crater floor. This peak is more than twice the height of Mount Everest and is one of the tallest mountains in the entire solar system. The impact that created Rhea Silvia was so violent that it excavated material from deep within Vesta's interior, exposing rocks that had not seen the surface in billions of years. Beneath Rhea Silvia lies an even older impact structure called Venonea, another enormous crater that has been partially obliterated by the later Rhea Silvia impact. These two giant impacts blasted enormous amounts of material off Vesta's surface and into space. Much of this material eventually fell back to Vesta, but some escaped into orbit around the Sun, becoming smaller asteroids in their own right. Astronomers have identified a family of asteroids called Vestoids that appear to be fragments of Vesta, sharing similar compositions and orbital characteristics. Some of these Vestan fragments have made their way to Earth as meteorites. A class of meteorites called Howardite-Eucrit Diogenite meteorites, or HED meteorites, have compositions that match Vesta's surface as observed by Dawn. This provides a direct physical connection between asteroids and meteorites, allowing scientists to study pieces of Vesta in laboratories on Earth. Analysis of these meteorites confirms Vesta's age at about 4.5 billion years, dating back to the very earliest era of the solar system. Dawn's observations also revealed unexpected features on Vesta's surface, including distinctive grooves and channels that encircle the asteroid's equator. These grooves appear to have formed as a result of the Rhea Silvia impact, which was violent enough to send shock waves completely through Vesta's interior, fracturing and deforming the crust on the opposite side of the asteroid. The discovery of these features demonstrated that even relatively small worlds like Vesta can experience geological processes more commonly associated with planets. The asteroid belt is not uniformly filled with asteroids, but instead contains distinct regions of higher and lower density. These variations in asteroid density are caused by orbital resonances with Jupiter, which create zones where asteroids cannot maintain stable orbits over billions of years. Understanding these resonances provides insight into the gravitational dynamics that have shaped the asteroid belt since the formation of the solar system. An orbital resonance occurs when the ratio between two objects' orbital periods can be expressed as a simple fraction. For example, if an asteroid orbits the Sun exactly 3 times for every 2 orbits completed by Jupiter, that asteroid is in a 3-to-2 resonance with Jupiter. At these resonance locations, the gravitational pull from Jupiter acts on the asteroid in a regular, periodic way, always pulling in the same direction at the same point in the asteroid's orbit. Over millions of years, these regular gravitational tugs add up, pumping energy into the asteroid's orbit. This increased energy typically increases the asteroid's orbital eccentricity, making its orbit more elongated. Eventually, the asteroid's orbit may become eccentric enough that it crosses the orbit of Mars or even Earth. When this happens, gravitational interactions with these planets can scatter the asteroid into a completely different orbit, or eject it from the solar system entirely. The result of this process is that orbital resonances act as a kind of drain, gradually removing asteroids from resonance locations over geological time. The most prominent resonances in the asteroid belt are called Kirkwood gaps, named after the American astronomer Daniel Kirkwood, who first identified them in 1866. The 3-to-1 resonance at about 2.5 astronomical units from the Sun creates a particularly pronounced gap where very few asteroids are found. The 5-to-2, 7-to-3, and 2-to-1 resonances also create noticeable depletions in the asteroid population. However, resonances do not always remove asteroids. Some resonances can actually trap and protect asteroids, keeping them in stable orbits for billions of years. The most famous example of protective resonances are the Trojan asteroids, which share Jupiter's orbit but remain about 60 degrees ahead of or behind the giant planet. These asteroids are trapped in what are called Lagrange points, locations where the combined gravitational pull of Jupiter and the Sun create stable equilibrium positions. The existence of Kirkwood gaps and Trojan asteroids demonstrates the powerful influence Jupiter continues to exert on the asteroid belt. Even 4.5 billion years after the solar system's formation, Jupiter's gravity is still sculpting the distribution of asteroids, slowly removing objects from resonance zones while protecting others in stable niches. This ongoing gravitational interaction makes the asteroid belt a dynamic, evolving region rather than a static collection of ancient debris. Modern computer simulations can model these resonance effects with remarkable precision. By calculating the orbits of thousands of simulated asteroids over millions of years, astronomers can reproduce the observed structure of the asteroid belt, including the locations of gaps and concentrations. These simulations confirm that Jupiter's gravitational influence, combined with occasional close encounters with Mars and other asteroids, is sufficient to explain the current distribution of asteroids without needing to invoke any additional forces or mechanisms. Not all asteroids in the belt formed where they currently orbit. Some asteroids appear to be interlopers that originated in different parts of the solar system and later migrated to the asteroid belt. Identifying these migrant asteroids and understanding their origins provides valuable information about the early evolution of the solar system and the processes that distributed material throughout the Sun's planetary system. The most compelling evidence for asteroid migration comes from the composition of outer belt asteroids. Many asteroids in the outer regions of the belt have compositions rich in water ice and organic compounds, similar to comets and to objects in the Kuiper belt beyond Neptune. These icy compositions are difficult to explain if the asteroids formed at their current locations, where temperatures would have been too high for water ice to condense from the solar nebula. The presence of these icy asteroids in the outer belt suggests they formed much farther from the Sun, possibly in the region where Uranus and Neptune now orbit, or even beyond. Early in solar system history, when the giant planets were still migrating and settling into their current orbits, gravitational interactions could have scattered large numbers of icy planetesimals inward. Some of these objects would have been captured into stable orbits in the asteroid belt, while others collided with the inner planets or were ejected from the solar system entirely. This scenario is supported by what is called the NICE model, named after the French city where it was developed. The NICE model proposes that the giant planets did not form in their current locations, but instead migrated significantly during the first few 100 million years of solar system history. Jupiter moved slightly inward, while Saturn, Uranus, and Neptune moved outward. This migration destabilized the orbits of countless icy planetesimals in the outer solar system, scattering them throughout the planetary system. Some of the scattered planetesimals would have been captured into the asteroid belt, particularly in its outer regions where their ice-rich compositions are now observed. This explains the presence of primitive, volatile-rich asteroids, like those in the C-type classification. It also explains why some asteroids have compositions that seem out of place for objects that should have formed at their current distances from the Sun. Recent studies have identified specific families of asteroids that may be captured interlopers from the outer solar system. These families share similar orbits and compositions, suggesting they originated from a single parent body that was captured into the asteroid belt and later broken up by collisions. By studying the properties of these families, astronomers can learn about the composition and structure of objects from the distant reaches of the solar system without needing to send spacecraft to those remote regions. The story of asteroid migration also works in reverse. Just as objects from the outer solar system were scattered inward into the asteroid belt, objects from the asteroid belt have been scattered outward and inward throughout solar system history. Some asteroids have been flung into the outer solar system, where they may masquerade as comets if they contain ice. Others have been scattered into the inner solar system, becoming near-Earth asteroids that occasionally cross Earth's orbit and pose potential impact hazards. This exchange of material between different regions of the solar system means that the asteroid belt serves as both a source and a sink for small bodies. It is a repository for material from throughout the solar system, a mixing zone where objects from different origins have come together and remain preserved in the freezer of space. Studying the diversity of asteroid compositions thus provides a window into the composition and structure of the entire solar system, from the hot inner regions near the Sun to the cold outer reaches beyond Neptune. The asteroid belt is organized not just by resonances and migration, but also by collisions. Over billions of years, asteroids have crashed into each other countless times, sometimes gently merging, but more often violently shattering. These collisions create what astronomers call asteroid families, groups of asteroids with similar orbits and compositions that originated from the breakup of a larger parent body. Identifying asteroid families allows astronomers to study the outcomes of different types of collisions and to understand the internal structure of asteroids. When a large asteroid is shattered by a collision, the fragments inherit similar orbits because they all start from roughly the same point in space with similar velocities. Over time, small differences in their orbits cause the fragments to slowly drift apart, but they remain clustered together in orbital space for millions or even billions of years. The Flora family, one of the largest and most prominent asteroid families, contains thousands of members that appear to be fragments of a single parent body that was destroyed by a collision perhaps a billion years ago. The members of this family share similar composition and orbit in a relatively compact region of the inner asteroid belt. By studying how the fragments are distributed and how their orbits have evolved, astronomers can work backward to determine when the collision occurred and how much energy was involved. Another important family is the Coronis family, which formed from the breakup of a parent body about 100 kilometers in diameter. This family is particularly interesting because some of its members show evidence of having been heated to high temperatures during the collision that created them. This heating altered their mineral structure in ways that can still be detected billions of years later, providing information about the violence of large asteroid collisions. Some asteroid families are very young in astronomical terms. The Datura family appears to have formed only about 500,000 years ago from a recent collision. The fragments of this family have not had time to drift far apart, so they remain tightly clustered in orbital space. Young families like Datura provide opportunities to study the immediate aftermath of asteroid collisions and to see how fragment orbits evolve over relatively short time scales. Asteroid families also provide natural laboratories for studying the strength and structure of asteroids. By examining how large a parent body was and how many fragments were created, scientists can estimate how much energy the collision involved and what this implies about the asteroid's internal structure. Some asteroids appear to be solid rocky bodies that shatter into relatively few large fragments when struck. Others appear to be rubble piles, loose collections of smaller pieces held together weakly by gravity, which break apart into many small fragments when hit. The study of asteroid families has also revealed that some large asteroids are themselves fragments of even larger parent bodies. Vesta, for example, is thought to be the largest remaining fragment of a family of objects that formed early in solar system history. The impacts that created Vesta's giant craters produced families of smaller vestoid asteroids, demonstrating a hierarchy of collisions and fragmentation that has shaped the asteroid belt throughout its history. One of the most surprising discoveries about the asteroid belt in recent decades has been the abundance of water. Far from being dry rocks floating in space, many asteroids contain significant amounts of water, either locked up as ice beneath dusty surfaces or bound into minerals as water of hydration. The presence of this water has important implications for understanding how Earth and the other terrestrial planets acquired their water and possibly their organic compounds. Ceres, as we have seen, may contain more fresh water than all of Earth's surface water combined, but Ceres is not unique in harbouring water. Many smaller asteroids also show spectroscopic evidence of water ice or water-bearing minerals on their surfaces. The Dawn spacecraft detected water-bearing minerals on Vesta's surface, delivered there by impacts from water-rich asteroids. Even relatively small asteroids have been found to outgas water vapor, suggesting they contain substantial ice in their interiors. The water content of asteroids varies systematically across the belt. Asteroids in the inner belt, closer to the Sun, tend to be drier because the higher temperatures in this region during solar system formation prevented water ice from condensing. Asteroids in the outer belt are much richer in water because they formed in a cooler environment where ice could persist. This variation in water content provides information about the temperature structure of the early solar nebula. Understanding the water content of asteroids is crucial for understanding how Earth got its water. Our planet formed in the inner solar system, where temperatures were high enough that water should have been vaporized. Yet Earth's oceans cover more than 70% of the surface, and water is abundant in rocks and the atmosphere. This water must have been delivered to Earth after it formed, and asteroids are one of the prime suspects for this delivery. Asteroids impact Earth much more frequently than comets, and some types of asteroids have water content and isotopic composition very similar to Earth's oceans. Computer simulations of the early solar system show that large numbers of asteroids from the outer belt would have been scattered into Earth-crossing orbits during the era of planetary migration. These asteroids would have bombarded the young Earth, delivering vast quantities of water along with organic compounds and other volatile materials. The discovery of water on asteroids also has practical implications for human space exploration. Water can be split into hydrogen and oxygen, providing rocket, fuel and breathable air for astronauts. It can also be used for drinking, growing food, and shielding against radiation. An asteroid mining operation could extract water from asteroids and use it to support human activities in space, eliminating the need to launch water from Earth's surface at enormous cost. Several companies and space agencies are already developing technologies for asteroid mining. These efforts focus initially on near-Earth asteroids, which are easier to reach than main belt asteroids, but eventually they might extend to the asteroid belt itself. The water and other resources locked up in asteroids could support a future space-based economy, providing the raw materials needed for construction, manufacturing, and life support throughout the inner solar system. Given everything we have learned about the asteroid belt from spacecraft missions, telescopic observations, and theoretical modelling, can we finally put the Phaeton hypothesis to rest? The scientific evidence overwhelmingly indicates that no planet ever existed in the asteroid belt. The total mass of the belt is far too small, the compositional diversity is too great, and the dynamical structure is inconsistent with planetary destruction. The asteroids are leftover planetesimals that never accreted into a planet because of Jupiter's gravitational interference. However, some intriguing observations have prompted scientists to reconsider whether the asteroid belt might contain evidence of lost protoplanets. These would not be full-size planets like the Phaeton of 19th century imagination, but rather planetary embryos, objects that grew to hundreds or even thousands of kilometers in diameter before being destroyed by collisions. Vesta, with its differentiated structure and ancient volcanic activity, is an example of such a planetary embryo that survived to the present day. Computer simulations of asteroid belt formation suggest that numerous Vesta-sized or larger embryos probably formed in the belt region early in solar system history. These objects would have grown quickly by accreting smaller planetesimals, differentiating into core, mantle, and crust structures, just like terrestrial planets. But unlike the terrestrial planets, which had time to grow into full-sized worlds, these asteroid belt embryos existed in a gravitationally violent environment dominated by Jupiter. The high-velocity collisions driven by Jupiter's gravitational stirring would have been catastrophic for these embryos. Instead of merging when they collided, as planetesimals do at low velocities, embryo collisions at high velocity would have shattered and fragmented both bodies. Over millions of years, this collisional grinding would have destroyed most of the large embryos, breaking them down into the smaller asteroids we see today. Vesta survived only because it was lucky enough to avoid catastrophic collisions. Evidence for these destroyed embryos may exist in the form of iron meteorites. These meteorites, which are chunks of metallic iron and nickel, appear to come from the cores of differentiated asteroids that no longer exist. Their existence implies that numerous embryos large enough to differentiate must have existed at some point, and that these embryos were later destroyed by collisions that scattered their cores into space as M-type asteroids. Some scientists have proposed that the asteroid belt might have contained embryos as large as Mars early in its history. These objects would have been true protoplanets, well on their way to becoming terrestrial planets if given enough time and material. But the timing of Jupiter's formation and migration prevented these embryos from growing further. Instead of becoming planets, they became victims of collisional destruction, ground down over hundreds of millions of years until only Ceres, Vesta, and a few other large asteroids remained. This revised view of the asteroid belt's history shares some elements with the old Phaeton hypothesis. There may indeed have been large planetary bodies in the asteroid belt that were destroyed by collisions. But these were not single planets that exploded or shattered in one dramatic event. Instead, they were numerous embryos that were gradually ground down by countless collisions over immense spans of time, a slow-motion destruction spread across hundreds of millions of years. The difference between this modern understanding and the original Phaeton hypothesis might seem subtle, but it is profound. The 19th century version imagined a single catastrophic event destroying a fully formed planet. The modern version describes a region where planet formation was disrupted from the beginning, preventing embryos from ever growing large enough to be called planets before grinding them down through collisional evolution. One is a story of planetary death, the other a story of planetary stillbirth. The asteroid belt is not isolated from the rest of the solar system, but constantly exchanges material with other regions, particularly the inner solar system where Earth orbits. Understanding this exchange is crucial for assessing the impact hazard that asteroids pose to our planet, and for understanding how asteroid impacts have shaped Earth's geological and biological history. Near-Earth asteroids are objects whose orbits bring them close to Earth's orbit. These asteroids originate primarily from the main asteroid belt, scattered into Earth-crossing orbits by gravitational resonances with Jupiter or by collisions with other asteroids. Once in the inner solar system, near-Earth asteroids typically survive for only a few million years before colliding with the Sun, a planet, or being ejected from the solar system. This means the population of near-Earth asteroids must be constantly replenished by new arrivals from the main belt. Astronomers have catalogued tens of thousands of near-Earth asteroids and estimate that hundreds of thousands more remain undiscovered. The largest of these objects, if they struck Earth, could cause global catastrophe, potentially threatening human civilization. Smaller asteroids strike Earth more frequently, but cause only local or regional damage. Objects just a few meters across enter Earth's atmosphere several times per year, typically burning up as bright fireballs without reaching the ground. The impact that wiped out the non-avian dinosaurs 66 million years ago was caused by an asteroid roughly 10 kilometers in diameter that struck what is now the Yucatan Peninsula in Mexico. The energy released by this impact was equivalent to billions of nuclear weapons, triggering global firestorms, mega tsunamis, and a long-lasting winter caused by dust and aerosols blocking sunlight. This single impact event fundamentally altered the course of life on Earth, ending the age of dinosaurs and creating opportunities for mammals to diversify and eventually give rise to humans. Asteroid impacts of this magnitude are extremely rare, occurring perhaps once every 100 million years on average. Smaller but still devastating impacts occur more frequently. The Tunguska event of 1908, which flattened 2,000 square kilometers of Siberian forest, was caused by an asteroid only about 50 to 100 meters in diameter that exploded in the atmosphere. Such events might occur once every few centuries. To protect Earth from future impacts, astronomers are conducting systematic surveys to find and track all potentially hazardous asteroids. Once an asteroid's orbit is known precisely, astronomers can predict whether it might strike Earth decades or even centuries in advance. This advance warning could allow time to develop and implement deflection strategies using spacecraft to nudge a threatening asteroid into a different orbit that misses Earth. Several asteroid deflection techniques have been proposed and tested. The most straightforward approach is the kinetic impactor. Essentially, a massive spacecraft crashed into an asteroid at high velocity to change its momentum. NASA's DART mission successfully demonstrated this technique in 2022 by deliberately impacting the asteroid Dimorphos and measurably altering its orbit. Other proposed techniques include gravitational tractors, where a spacecraft hovers near an asteroid and uses its own gravity to slowly tug the asteroid into a new orbit, and nuclear devices that would vaporize material from an asteroid's surface, creating a jet that pushes the asteroid in the opposite direction. Despite decades of study and multiple spacecraft missions, the asteroid belt still harbors many mysteries. Each new discovery raises new questions and reveals unexpected complexity in this region that was once dismissed as mere debris. Some of the most intriguing current mysteries include the origin of asteroid volatiles, the population of very small asteroids, and the possibility of previously unknown types of asteroids waiting to be discovered. The presence of ice and organic compounds on asteroids like Ceres suggests these objects retain volatiles that should have been lost over billions of years. How have these materials survived for so long? Sublimation, the process by which ice turns directly into vapor without melting, should have removed surface ice from asteroids long ago. The fact that ice persists suggests it is constantly replenished from reservoirs deeper inside asteroids, but the mechanisms driving this replenishment are not fully understood. Another mystery involves the population of very small asteroids, those measuring only a few meters to a few tens of meters across. These tiny objects are too faint to be detected by Earth-based telescopes, but they are numerous and potentially important for understanding collisional evolution in the belt. Spacecraft missions have photographed small asteroids at close range, revealing them to be irregularly shaped, often elongated or potato-like, with surfaces covered in boulders and debris. Understanding how many of these small asteroids exist and how they interact would improve models of asteroid collisions and evolution. The discovery of active asteroids that develop comet-like tails of dust and gas has challenged traditional distinctions between asteroids and comets. These objects orbit in the asteroid belt, but occasionally display activity more typical of comets. The cause of this activity is not always clear. Some active asteroids appear to be releasing dust through sublimation of ice, while others might be shedding material due to rapid rotation or even small impacts. These hybrid objects blur the line between asteroids and comets and suggest that the solar system's small bodies are more diverse than simple classification schemes suggest. Recent observations have also revealed that some asteroids have their own moons or exist as binary systems where two similarly sized objects orbit each other. About 15% of near-Earth asteroids appear to be binaries, and several main belt asteroids are known to have small satellites. The formation of these binary systems is not fully understood, though models suggest they might form when a rapidly rotating asteroid breaks apart due to centrifugal force, or when two asteroids collide gently at low velocity and remain gravitationally bound. Questions also remain about the early evolution of the asteroid belt and how much material it originally contained. If Jupiter's gravitational influence prevented planet formation in the belt, how much mass was scattered away? Was the early asteroid belt 10 times more massive than today, or 100 times, or even 1,000 times? Different models give different answers, and distinguishing between them requires detailed simulations that account for complex gravitational interactions between planets, asteroids, and the gaseous solar nebula. Perhaps the deepest mystery is whether life might exist on asteroids. Ceres has water, continue organic, compounds, and geological activity, the basic ingredients often considered necessary for life. Could simple microorganisms exist in the dark, liquid water ocean beneath Ceres's frozen crust? Could similar conditions exist on other large asteroids we have not yet explored? While most scientists consider asteroid-based life unlikely, the question cannot be definitively answered without further exploration, and possibly even drilling missions to sample subsurface environments. The asteroid belt also holds clues to planetary formation processes throughout the galaxy. As astronomers discover more exoplanetary systems around other stars, they are finding that many of these systems have architecture very different from our own solar system. Some have giant planets orbiting close to their stars, while others have chains of rocky planets with no gas giants at all. Understanding how Jupiter's presence shaped our asteroid belt helps astronomers interpret the structure of these alien planetary systems and understand the diversity of possible outcomes from planet formation. The exploration of the asteroid belt is far from complete. While the Dawn mission provided unprecedented views of Ceres and Vesta, these two objects represent only a tiny fraction of the belt's diversity. Dozens of other large asteroids await detailed exploration, each potentially harboring unique geological features and scientific discoveries. Future missions will continue to reveal the secrets of this fascinating region. NASA's Psyche mission, launched in October 2023, is currently traveling to the asteroid 16 Psyche, one of the largest M-type or metallic asteroids in the belt. This mission will test the hypothesis that Psyche is the exposed iron core of a shattered protoplanet, offering a unique opportunity to study material normally hidden deep inside planetary bodies. Observations of Psyche's surface, magnetic field, and composition will provide insights into how planetary cores form and differentiate, processes we cannot study on Earth because our planet's core lies thousands of kilometers beneath the surface. The European Space Agency has proposed several asteroid missions as well, including concepts to visit primitive carbonaceous asteroids that may contain pristine material from the solar system's formation. These missions would complement NASA's efforts by targeting different types of asteroids, building a comprehensive picture of the belt's compositional diversity. Some proposals include sample return missions that would bring pieces of asteroids back to Earth for detailed laboratory analysis. Private companies are also planning asteroid missions, motivated by both scientific curiosity and commercial interests. Several startups have announced plans to mine asteroids for water, metals, and other resources, though the technical and economic challenges remain formidable. Even if commercial asteroid mining proves impractical in the near term, the technologies developed for these ventures could enable more ambitious scientific missions and help build infrastructure for deep space exploration. Future human missions to asteroids are also being planned. NASA's Artemis program includes provisions for eventual human missions beyond the Moon, with near-Earth asteroids as potential destinations. Visiting an asteroid would provide valuable experience for longer-duration missions to Mars, while offering opportunities for astronauts to conduct hands-on geological fieldwork in an environment very different from any planet. The microgravity conditions on asteroids would present unique challenges for astronauts, but also unique opportunities for conducting experiments impossible on Earth. Advances in telescope technology will also revolutionize asteroid science from Earth. New facilities like the Vera Rubin Observatory, currently under construction in Chile, will conduct systematic surveys of the entire visible sky every few nights, detecting thousands of new asteroids and tracking their orbits with unprecedented precision. These surveys will discover most of the remaining large asteroids and many smaller objects, providing statisticians with the data needed to understand the size distribution and population of the belt. Infrared space telescopes will complement visible light observations by detecting the heat radiated by asteroids. Since an asteroid's temperature depends on its size, distance from the Sun, and surface properties, infrared observations can determine asteroid sizes and compositions more accurately than visible light alone. The James Webb Space Telescope has already begun observing asteroids as part of its science program, and future dedicated infrared missions could map the thermal properties of thousands of belt asteroids. Perhaps the greatest value of the asteroid belt lies not in its resources or impact hazard, but in its role as a cosmic museum preserving samples from the solar system's earliest days. Because asteroids never grew large enough to melt and differentiate completely like planets, many of them retain primitive materials, largely unchanged since the solar nebula collapsed 4.5 billion years ago. Studying these materials provides direct evidence of the conditions and processes that gave birth to our planetary system. Meteorites that fall to Earth from the asteroid belt carry this ancient heritage in their atoms and minerals. Some meteorites contain pre-solar grains, microscopic particles that formed around other stars before our Sun even existed. These grains survived the formation of the solar system and were incorporated into asteroids, where they remained preserved until collisions ejected them toward Earth. Analyzing pre-solar grains allows scientists to study the composition of ancient stars and the nucleosynthetic processes that created the elements. Other meteorites contain calcium-aluminum inclusions, some of the first solid materials that condensed from the solar nebula. These inclusions are older than the planets themselves, dating back to the very beginning of solar system formation. Their mineral compositions record the temperature and chemical conditions in different parts of the early solar nebula, providing constraints for models of how the Sun and planets came together from collapsing gas and dust. Organic compounds found in carbonaceous meteorites demonstrate that the building blocks of life were present in the early solar system and were delivered to Earth by asteroid impacts. These compounds include amino acids, the building blocks of proteins, and nucleobases, the building blocks of DNA and RNA. While this does not prove that life originated from asteroid-delivered organics, it shows that the raw materials were available and that asteroid impacts could have contributed to the chemical complexity of the young Earth. Some meteorites contain tiny diamonds formed by the shock and pressure of asteroid collisions. Others contain minerals that could only form in the presence of liquid water, indicating that water flowed inside asteroids billions of years ago. Still others show evidence of magnetic fields, suggesting their parent asteroids once had active dynamos generating magnetism from liquid iron cores. Each meteorite is a messenger from a different asteroid with a different history, collectively telling the story of an entire region of the solar system. The asteroid belt also serves as a laboratory for studying planetary processes under conditions different from those on Earth. The low gravity on asteroids affects how impact craters form and how regolith develops. The extreme temperature variations between sunlit and shadowed regions drive thermal stresses that fracture rocks in ways not seen on planets with atmospheres. The near-perfect vacuum allows some chemical reactions while preventing others. Understanding these alien environments expands our knowledge of how geological processes work and prepares us for exploring other low-gravity bodies throughout the solar system. Placing the asteroid belt in the broader context of the solar system reveals its unique position and importance. The belt marks a transition zone between two fundamentally different types of planets. Interior to the belt are the terrestrial planets, small rocky worlds with solid surfaces, thin atmospheres, or no atmosphere at all, and relatively high densities. Exterior to the belt are the giant planets, massive worlds composed primarily of hydrogen and helium or ice, with deep atmospheres and much lower densities. This transition reflects the temperature structure of the early solar nebula. Close to the young Sun, temperatures were high enough that only rocky and metallic materials could condense into solid particles. These materials are relatively rare in cosmic abundances, so the inner planets remained small. Farther from the Sun, beyond what astronomers call the frost line, temperatures dropped low enough for water ice to condense. Since water is much more abundant than rock and metal, the planets that formed beyond the frost line could grow much larger, eventually becoming massive enough to capture hydrogen and helium gas directly from the nebula. The asteroid belt straddles this frost line, with its inner regions dominated by dry, rocky asteroids and its outer regions containing increasing amounts of water ice and organic compounds. This gradient in composition records the temperature gradient in the early solar nebula and shows how conditions varied with distance from the forming Sun. Studying this compositional gradient helps astronomers understand the processes that distributed materials throughout the planetary system. Compared to asteroid belts observed around other stars, our asteroid belt is relatively low in mass. Many young stars are surrounded by much more massive debris disks that might eventually form planets or might remain as dense asteroid belts. Our belt's low mass is likely a consequence of Jupiter's early formation and migration, which scattered away most of the material that initially existed between Mars and Jupiter. This makes our asteroid belt somewhat unusual among planetary systems, but also makes it representative of mature systems where giant planets have cleared out debris. The asteroid belt's influence extends throughout the inner solar system through its role as the main source of meteorites and as a reservoir for near-Earth asteroids. The steady supply of material from the belt to Earth and the other terrestrial planets has continued throughout solar system history, delivering water, organics, and other materials while also causing destructive impacts. This ongoing exchange links the fates of the terrestrial planets to events in the asteroid belt, making the belt an integral part of the inner solar system's evolution rather than an isolated region. Beyond its scientific importance, the asteroid belt has captured human imagination and influenced popular culture in ways that often diverge from scientific reality. Science fiction stories frequently depict the asteroid belt as a densely packed obstacle course where spacecraft must dodge and weave through a storm of tumbling rocks. This portrayal makes for exciting visuals, but bears little resemblance to the actual belt, where asteroids are typically millions of kilometers apart, and a spacecraft could traverse the entire region without coming close to any asteroid unless deliberately aimed at one. The idea of asteroid mining has become a staple of science fiction, imagining future economies based on extracting valuable metals and resources from asteroids. While technically challenging, asteroid mining is not impossible, and some of the richest deposits of platinum, gold, and other rare metals in the solar system might indeed exist in metallic asteroids. Whether these resources can ever be extracted profitably remains an open question, but the concept has inspired serious engineering studies and even corporate ventures. Asteroids have also featured prominently in disaster scenarios, from movies depicting civilization-ending impacts to news reports of close approaches by potentially hazardous asteroids. While the asteroid impact threat is real and deserves serious attention, the actual risk is often exaggerated or misunderstood in popular media. Statistical analysis shows that an individual person is far more likely to die from common hazards than from an asteroid impact, though the consequences of a large impact would be catastrophic for civilization as a whole. The naming of asteroids has created its own cultural legacy. Unlike planets, which are named after Roman gods, asteroids have been named after a vast array of people, places, concepts, and even fictional characters. There are asteroids named after scientists, musicians, authors, cities, universities, and mythological figures from cultures around the world. This democratic approach to naming reflects the sheer number of asteroids and the many different discoverers who have contributed to mapping the belt. Some asteroid names commemorate important historical figures or events. Others honor contributors to science and culture who might otherwise be forgotten. Still others reflect the personal interests and humour of their discoverers, resulting in asteroids named after favourite foods, beloved pets, or characters from literature and film. This diverse nomenclature makes the asteroid belt a kind of celestial hall of fame, preserving in the heavens the names of people and things deemed worthy of remembrance. As human civilization expands beyond Earth, our relationship with the asteroid belt will necessarily evolve. The belt will transition from being merely a subject of scientific study to becoming a destination for exploration, a source of resources, and perhaps eventually a region of human habitation. Understanding and preparing for this transition requires thinking carefully about the opportunities and challenges that asteroids present. The resources contained in asteroids could support human activities throughout the solar system. Water extracted from asteroids could be split into hydrogen and oxygen for rocket fuel, eliminating the need to launch fuel from Earth's deep gravity well. Metals could be used for construction in space, building habitats, solar arrays, and spacecraft without the expense of lifting materials out of Earth's atmosphere. Even the dust and small rocks on asteroid surfaces might find uses as radiation shielding or as raw material for three-dimensional printing in space. However, exploiting these resources will require overcoming significant technical challenges. Asteroids have almost no gravity, making it difficult for equipment and workers to stay in place while conducting mining operations. The lack of atmosphere means there is no air to breathe and no protection from solar radiation. Extreme temperature variations between sunlight and shadow create thermal stresses on equipment. Communication delays of tens of minutes between Earth and the asteroid belt mean that operations must be largely autonomous or managed by humans living in the belt itself. Legal and ethical questions also arise when contemplating asteroid utilization. Who owns asteroids and who has the right to extract their resources? The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies, but it is less clear about private ownership and commercial exploitation. Various international agreements and national laws attempt to address these questions, but comprehensive legal frameworks for space resource utilization are still being developed. Environmental considerations apply even in the vacuum of space. Should asteroids be preserved in their natural state for scientific study, or are they simply resources to be used? If an asteroid harbours unique geological features, or might contain evidence of past or present life, should it be protected from industrial exploitation? These questions echo similar debates on Earth about wilderness preservation versus resource development, but in space, the stakes and contexts are entirely different. The possibility of establishing permanent human settlements in the asteroid belt raises even more profound questions. Could people live healthy, fulfilling lives in the microgravity environment of asteroids, or would the lack of gravity cause unacceptable health problems? How would communities in the belt govern themselves and maintain connections to Earth across communication delays of tens of minutes? What would motivate people to leave Earth for such a challenging environment, and what kind of society might develop in the belt? The mystery of the asteroid belt between Mars and Jupiter has evolved dramatically over the past 2 centuries. What began as a search for a missing planet predicted by mathematical patterns has become an exploration of a complex, diverse region that preserves clues to the solar system's formation and evolution. The belt is not the remains of a destroyed planet, but rather a collection of planetesimals that never accreted into a planet because of Jupiter's gravitational dominance. The objects in the asteroid belt range from dust particles to the dwarf planet Ceres, with compositions spanning from dry rock to water-rich ice. They occupy a region of space sculpted by gravitational resonances, shaped by billions of years of collisions, and continuously exchanging material with the rest of the solar system. Some asteroids are primitive bodies largely unchanged since the solar nebula, while others like Vesta are differentiated worlds with geological histories rivaling those of planets. Far from being empty space or simple debris, the asteroid belt is a dynamic, evolving region that continues to surprise scientists with its complexity. Missions like Dawn have revealed active geology on Ceres, ancient volcanism on Vesta, and compositional diversity that reflects the varied origins and histories of different asteroids. Future missions will continue this exploration, visiting metallic asteroids, carbonaceous asteroids, and perhaps eventually returning samples from multiple belt objects for detailed laboratory study. The asteroid belt also serves practical purposes beyond scientific curiosity. It provides a natural laboratory for studying impact processes, planetary formation, and the behavior of materials in extreme environments. It supplies meteorites that bring pieces of the solar system's history to Earth for study. It harbors resources that might support future space exploration and development. And it poses a real, if statistically small, impact hazard that requires ongoing monitoring and eventual development of planetary defense capabilities. Perhaps most fundamentally, the asteroid belt reminds us that the solar system is far more complex and interesting than simple diagrams of 9 planets orbiting the Sun. The belt is a region with its own character and history, neither planet nor empty space, but something unique. It challenges our tendency to classify everything into neat categories and forces us to recognize that nature often produces intermediates and exceptions that defy simple classification. The story of the asteroid belt is also a story about how science progresses. The Teachus Bode law seemed to work until it did not, teaching astronomers to be skeptical of mathematical patterns that lack physical explanations. The Phaeton hypothesis seemed plausible until detailed observations ruled it out, demonstrating the importance of testing ideas against evidence. Each generation of astronomers has refined our understanding of the belt, building on previous work while correcting earlier misconceptions. Looking forward, the asteroid belt will remain a frontier of exploration and discovery for decades to come. New missions will visit unexplored asteroids, revealing unexpected features and raising new questions. New technologies will enable more sophisticated observations from Earth and eventually from human outposts in space. New theories will be developed and tested, advancing our understanding of how planetary systems form and evolve, not just in our solar system, but throughout the galaxy. The belt also represents a possible future for humanity beyond Earth. While Mars captures most public attention as a destination for human exploration, asteroids offer their own advantages as stepping stones into the solar system. They are easier to land on and take off from than planets because of their low gravity. They contain valuable resources. They are numerous and diverse, offering many different environments and opportunities. A future where humans inhabit the asteroid belt, building communities among these ancient worlds, is not inevitable, but neither is it impossible. What would Giuseppe Piazzi think if he could see what his discovery on that first night of 1801 has led to? That faint point of light moving through Taurus has been revealed as an ocean world with active geology and possible subsurface habitability. The missing planet he thought he had found turned out to be the largest member of a vast population of objects representing the building blocks from which planets form. His discovery opened up an entire region of the solar system to human knowledge and possible future exploration. The asteroid belt stands as proof that the universe often confounds our expectations. We looked for a planet and found thousands of worlds too small to be planets. We expected dead rocks and found active geology, water oceans, and perhaps the ingredients for life. We thought we understood planetary formation and then had to revise our theories to account for what we found in the belt. Each answer raises new questions, ensuring that the mystery of the asteroid belt will continue to engage and challenge scientists for generations to come. In the end, the greatest mystery of the asteroid belt may not be what happened to the planet that never was, but what these ancient worlds can teach us about where we came from and where we are going. Every asteroid is a time capsule containing evidence from the solar system's birth. Every meteorite that falls to Earth brings a message from that distant time. Every mission to the belt reveals new wonders and new puzzles. The asteroid belt is not a wasteland or an afterthought, but a treasure house of scientific knowledge and a possible pathway to humanity's future among the stars. The mystery endures not because we lack answers, but because each answer reveals deeper questions about the nature of planetary systems, the processes that shape worlds, and our place in the cosmos. The asteroid belt between Mars and Jupiter will continue to challenge us, surprise us, and inspire us for as long as we continue to look upward and wonder what secrets the darkness holds.